If you work in AI or ML, you've probably heard of sparse autoencoders, or SAEs, but have you ever wondered what they are precisely? In this video, Alejandro, who is a founding engineer at ZeroEntropy, explains what SAEs are in detail.
You may ask, how is this possible? We've been struggling to understand what it is that not just LLMs, but machine learning models in general, neural network models in general, do under the hood for quite some time, and they seem to be something of a black box. The hypothesis, which people generally call superposition, is that the dense models that we actually have are something of like a low dimensional projection of a much higher dimensional, that is many more parameters, models, which in that space are very interpretable. Like they decompose all of the human interpretable concepts into like single neurons, and they just do very basic matrix multiplications where like the enormous majority of the neural network is not actually active at any point in time. And in theory, this should be impossible. You should not be able to encode more features than you have dimensions in a single layer without some kind of loss. And the hypothesis is that the way that actual models approximate this is by making features nearly orthogonal in activation space. So instead of having like, an angle of 90, they'll have one of like 87 or something like that. And that way you can fit exponentially more information into a much, much smaller space. Again, coming back to this idea of machine learning models, LLMs, as like compression models. A few other terms we have to get out of the way before delving into the deep dive. The SAE's latent layer, the hidden layer, we're going to call the dictionary, just to avoid confusion. Hidden layer will refer to the hidden layer of the base LLM that the SAE is trying to understand. And overcompleteness refers to the fact that the SAE's dictionary is usually much, much larger than that activation dimension. That is the dimension of the hidden layer of the LLM. Very often that's like 32 times or 64 times. I've seen up to like 256. A feature is like a single neuron in that SAE hidden layer. And we'll get back to the rest of these, but just to give you some understanding of what this actually looks like. Here on the left, we have this vector x, and this can be the activations of any particular layer of a transformer model, let's say. Commonly that'll have a dimensionality of like 2048 or 4096. And the SAE's goal, it's this 3 parts here in the middle, is just to reconstruct that activation vector exactly. So is to put those activations back into the feed-forward step of the transformer model. Hence, autoencoder. The target reconstructed output is the same as the input. Now, this is not a particularly difficult task. Autoencoders have been used for many different purposes for quite a long time. Usually, however, the whole point is feature extraction or compression. That is to say, the dictionary of the autoencoder, this middle bit, is of a lower dimensionality than the dimensionality of the input and equivalently the output vectors. Here, however, it is overcomplete. It is much, much larger. And the reason why we would want that is because we want to introduce another penalty term into our loss reconstruction. The way that we want to reconstruct this input activation vector is by having only a few of the SAE's hidden layer activations, that is its dictionary features, be active at any one time. And hopefully, the hypothesis is that this will lead to a disentangling of the superposition. and that we will be able to like extract monosemantic features, neurons which correspond to only one concept. Neuron in the SAE dictionary that only hits when you're talking about, for example, Miley Cyrus, or only about the Golden Gate Bridge, or more generally talking about, like, let's say, architecture, or only when it's talking in French but not in like Spanish or Catalan, so on and so forth. In normal models, dense models, almost every neuron is polysemantic. Every neuron fires for almost every possible input text, and it's very hard to distinguish, like saying in a normal machine learning models, like in a random neuron from any random layer of an LLM, like, oh, this is the neuron that deals with, like, you know, math or sound engineering or like discussions of waterfalls in Venezuela. They just sort of all fire for basically everything with varying levels of strength, but it's very hard to like discern what's actually going on. That's polysemanticity. We want monosemanticity. Now, theoretically, the way in which we want to do this is to just restrict the number of non-zero activations. That's the whole definition of sparsity, through something called L0 loss. And this is literally just the count of how many of those SAE dictionary features are active for any given activation. Now, you will note that that is non-differentiable, and therefore it is difficult to use it as part of like our standard backpropagation algorithm. As such, most researchers use L1 norm as a differentiable convex proxy for L0, or just top K. In other words, we keep only the K largest activations from the SAE dictionary, and we ignore all of the rest, and then we just do the backpropagation on those. Empirically, this has seemed to work better, and most people have moved on to top K for this reconstruction loss, but we'll get there. Now, a little more on this idea of superposition, right? So if you think about the absolute simplest case of, let's say we have a model that just has like 2 parameters, and they encode basically for, a vector in like 2D space. And you want to encode many bits of information into that. Well, it's impossible if you demand that they be binary, right? In other words, if you want them to look like the image on the top left here, where there is perfect orthogonality. However, the intuition, basically, if you want like a geometric representation of this, is to just fit more of these by demanding that they don't have to be mutually orthogonal. And the reason why this would work is that only very rarely, like at a large scale, do concepts interfere with each other. Like you can have a neuron that simultaneously encodes for, recognizing that something is a dog, like if we're in an image captioning model or something like that. You can have a polysemantic neuron which determines, oh, this is a dog, this is a cat, this is a fox, so on and so forth. Or more commonly, like a neuron will simultaneously encode for, oh, this is like the snout of a dog and this is the transmission of a car. And the reason why that works is because those two concepts only come up together very rarely. And so you very rarely have a situation where like you need to disentangle those two for a single input. And so the model performance is just as good as if it had many more neurons which independently encoded for each of those. And essentially what SAEs are trying to do is to just decompose this back into almost pure orthogonality. And hopefully that would give us information as to what's actually going on in the model and be able to do some very, very cool applications with this technology. For those of you that are interested, here are the formal mathematical definitions of what we're actually doing. So the encoder and decoder steps of an SAE are nothing particularly special. They're just, your standard ReLUs over the encoding matrix. And reconstruction loss itself is usually just MSE loss, like it's nothing out of the ordinary. We're just trying to reconstruct the input vector as well as we can. The only real difference is that we add this sparsity penalty, this L sparse, where lambda here is just a hyperparameter for how strongly you want to enforce sparsity. And then the L1 penalty, again, is this notion of like how many of your SAE dictionary features are active at any given point in time.